Berkeley Labs Friends of Science sponsored talks, Science at the Theater. My name is Alan Chen. And I'm a science writer at the Lawrence Berkeley National Laboratory. Let me thank you for your interest in the research that's being done at Berkeley Lab. And first I'd like to thank the co-sponsors of these talks, the University of California, Berkeley, the Chabot Space and Science Center, the Exploratorium, the Osher Lifelong Learning Institute at Berkeley, the Lawrence Hall of Science, and the science departments of the Albany, Berkeley, and Oakland high schools. So our speaker, whom I will say a little more about in a moment, is a scientist at the lab's Environmental Energy Technologies Division. And this is a group of researchers that has been around since the 1970s, 73 in fact. For the last more than 30 years, we have been developing energy-efficient technologies that help reduce greenhouse gas emissions and help you save money on your energy bill. Some of these technologies are in your houses or may already be in your houses. If you have energy-efficient windows, the kind with the coatings on them that help you save energy, those were developed in our division in the 1980s in cooperation with the windows industry. We've also developed electronic ballasts, which are a component of fluorescent lamp systems. They help save energy and they reduce the hum of lighting systems. And they were an enabling technology of compact fluorescent lamps, CFLs, which I suspect that a number of you have in your homes. So we've been developing these energy-efficient technologies for more than 30 years now. There's more to come. And if you're interested in finding out more about those, take a look at our website, eetd.lbl.gov. Let me tell you a little bit about Marianne Piette. Marianne Piette is a staff scientist at Lawrence Berkeley National Laboratory and the research director of the Demand Response Research Center, which is funded by the California Energy Commission's Public Interest Energy Research Program. She's also the deputy group leader of the Commercial Building Systems Group. And she's been at the lab for quite a while now, since 1983, and she has extensive experience evaluating the performance of the energy efficiency performance of large buildings and has about 100 publications to her name in this area. The Demand Response Research Center, Marianne is going to tell you more about what demand response is, but the center is 4 years old, and it manages and conducts and disseminates research on demand response technologies. She completed her undergraduate work at UC Berkeley in physical science. She has a Master's of Science degree in mechanical engineering, also from UC Berkeley, and a licentiate in building services engineering from the Chalmers University of Technology in Sweden. In 2006, she received the Benner Award from the National Conference on Building Commissioning. Please join me in welcoming Marianne Piette to the stage.
Left my water here. Thanks, Alan. I want to thank everybody for spending the time to join me tonight in thinking and learning about the electric grid in California. I'm going to be focusing on the California energy system and talking about both the supply side and the demand side of electricity use. I also want to thank the folks at the lab who are putting this series on and thank them for inviting me to give you the opportunity to hear about what I'm going to be talking about. The work that I'm talking about today is sponsored primarily by the California Energy Commission. I also collaborate with the utilities in California, with SoCal Edison, San Diego Gas and Electric, and the Pacific Gas and Electric Company. I have this device here, which I'm going to use to advance my slides, and I'm going to give you a quick introduction into this world that we call it demand response because the demand responds at times when the electric grid is constrained. And that's what we mean by the word demand response. But I'm going to use a variety of terminology through the presentation. I'm going to try to make sure that I introduce that technology and help you understand the basic ideas from an engineering perspective and from a science perspective. The electric grid in California is a system that's growing. So the system is becoming peakier. On hot summer days, we use more and more electricity. We use it for cooling, and then the inland growth out near Palm Springs and the whole Central Valley is growing the peak. Our peak is growing faster than the energy use. So while we spend a lot of time talking about energy efficiency, the main thing I'll be doing in my research and that I'll be sharing with you is the idea of reducing peak on those hot summer days. And I'll talk about some of these devices that I brought to you here, and I'm going to start with some terminology. The electric systems, we talk about both energy and power. So power is the instantaneous system for electricity. So like we all know what a 100-watt light bulb is. That's the power it uses when it's on. If you took 10 of those light bulbs and ran them for an hour, that'd be a kilowatt hour. So on your utility bill, it has the energy that you consume. It actually doesn't tell you what your peak is. It doesn't tell you how much you use at the most one time. That's what power is. So we care about the power and the energy. But what I'm focusing on savings at peak times is the power. So we care a lot about when everybody uses their power at the same time, and that's typically the hot summer days in California. I'm going to give you a little bit of introduction on the history of what's been going on in California, talk about the research that we've been doing to try to address those hot summer days, and then talk about the future and hopefully introduce some ideas to you about technologies that we think are going to be coming into your house and let you know what's going on with utilities in California, because there's actually a lot going on in California, and it's happening around the world, but a lot of the things that we're doing at LBNL, you're going to see in California first, you'll see around the country. Now, one of the interesting things about power is there's a variety of units that we use, and I'll be using some of these terms in the talk. I'll be talking about kilowatts and megawatts and gigawatts. So a watt is on the scale of a light bulb, 15 watts for a compact fluorescent, 100 watts for an incandescent bulb that we all know is the traditional light bulb. A kilowatt is similar to what we use in a home. So when you have air conditioning, it actually can use up to 5 or 6 kilowatts. Many big homes will use more. And then large buildings, like the big Oakland Federal Building, which I'll be talking about a little bit more, that building uses about 5 megawatts. So we do this in scales of thousands: watts, kilowatts, megawatts, and gigawatts or gigawatts. California, the entire state, uses about 50 gigawatts. And in China, they're building about 50 gigawatts a year right now. So around the world, the electric systems are all growing. And in California, we're doing a lot to try to address the energy efficiency every day, but also address those peak times. This is the hourly load shape of California's loads. And there's 8,700 hours in a year, 8,760. And this is a plot that shows you from January all the way through November. And over here, you can sort of see it on the edge there. This is megawatts, or this 40, 50, 60 gigawatts. So in 2006, we got over 60 gigawatts. That was an all-time peak, and many of you may remember we had a heat storm in July, and there were several days of hot weather. And when we have several days of hot weather, we have air conditioning loads up and down the state that are peaking. And we had some very hot weather at that time. 2007 was not as hot as 2006, so we didn't hit this peak that year. But in general, California is becoming peakier. As I said, we've got a lot of inland growth, and the peak is growing faster than the energy use. Now, the shape here you see is actually weeks and weekends. So it goes up. So there's actually 52 of these little blips here through the year. And you can see in the winter time, we use less than 40 gigawatts. We get over 60 through the summer, and then we come down again. In California, the 3 big utilities are the majority of the electricity, but we have something called the independent system operator up in Folsom. And the independent system operator, it's like managing a water system. They manage how much gets pumped into the electric grid, and they try to make sure it's maintained, that the frequency on the grid is maintained. So we care a lot about those peak days, because what happens is the pipes are only so big, and they can only handle so much. And as we reach those peaks, the transmission and distribution system gets overloaded. We have to build new power plants. So those peaks drive the capacity of the system. We need more transmission, we need more distribution, and we need more power plants. So while we spend a lot of time thinking about solar and energy efficiency, the peak actually has a big influence on the cost of the electric system, and we want to bring down the demand side on those days as much as we can. This is what's called a load duration curve. And if you take all those hours, 8,760 hours, and you stack them from the lowest hour to the highest hour, you get a curve that looks like this. So here in winter, remember we use around 33,000 megawatts or 33 gigawatts. And this peak of 50 now, it's not 60 because the ISO has different boundaries depending on whether or not we include the municipal utilities like SMUD, the Sacramento Municipal Utility District, and Los Angeles Department of Water and Power. So we have a shape of a curve. What's interesting about this curve is these last 5 megawatts, 5 gigawatts, 5,000 megawatts is very steep. So you can see only less than 1% of the time, only 57 hours a year are we in that last 5 gigawatts. That's very expensive to have all that infrastructure for just those peak days. So we have a big system to support only a few hours a year. We have that system, as I mentioned, the transmission, the distribution, and the power plants for those that big peak there. And even 279 hours a year are we above 40,000 megawatts here. So this peak here is what we're trying to do with what we call demand response or shedding load. We want to shed that load, and we want to get the demand side to do something those special hours. So what we've been doing is working with the utilities in California to let people know. And right now, the utilities have thousands of customers, actually, that get phone calls, and they get emails, and they get notification. They get these orbs, and they get systems to tell them, today's a special day. Would you please change your lights, change your air conditioner setting, and reduce the load on your building? This here is a orb. This is a PG&E Energy orb. SoCal Edison gives these out also. These are notification devices. So they don't do anything except change color. And they are blue because it's a normal day. But they will turn orange and red on the day, orange the day before the event, and then red when you are being told to turn things off or to change your set points. And we'll talk about what you actually do. But we're going to change the building's loads, and we're going to let our orb sit there. Now, funny thing about the orb, these are LED lights in here, and this orb, it actually gets a cell phone signal. And I'm going to unplug it, and you're going to watch it's going to reboot. So it's going to turn blue. It may not turn blue. It took about an hour to find the signal. But it's blue right now, and it actually has these 3 power modes. It has this is low power mode, medium, and a high power mode. And we measured the power. It uses less. It doesn't get to our 1-watt standby, which we like plug-in devices to get to. So this orbs actually use about 3 watts, depending on what color LED it is. And I'm going to unplug it, and you can watch it change colors. These were initially developed for stock traders. So these are ambient notification devices that sit in the background, and they inform you of things going on, like stocks changing price levels, trigger points to buy stocks. And again, these are what we call notification devices. And a lot of the buildings that we're working with actually have these orbs. So you might ask somebody if they have an energy orb if they're in a big building. So I'm going to unplug it for you and just let you see what it does. What it's going to do is it's going to go through a series of colors as it finds the signal again. So it's looking for the signal, and it may take more than a half an hour to actually find it, and it's going to go through all the color changes. It's not, there you go. Now you get to see the orb colors. Now, the most important thing that we've been doing over the last few years is automation. So we don't want just orbs, because sometimes the person who knows what the orb is isn't there, and they might be out golfing or fishing. And we've been doing a lot of work over the last few years using the internet to automate the electric load shedding. We use this little box here, which I brought with me, which is in the picture. And this box takes internet signals to relay points. And we've got about a couple hundred of these in the PG&E service territory. So instead of getting a phone call or getting an email, you actually get that as well, but you also get some internet signals that come to the box. The signals are continuous. So our boxes, we have these boxes in many places, and if a building has newer control system, we actually don't need the box at all. So when we did this at Walmart and Walmart and Target, we didn't need the box. And I'll tell you about how we did that. But we have one at 3 IKEAs have the box. We have one of these boxes at Chabot Space Sciences. We have them at some high schools, Contra Costa, office buildings, and I'll show you some of the buildings in some of the pictures. But the box is basically taking internet signals, and the building is then pre-programmed to do something when the signals come in. So looking at my picture over here, I have a laser pointer here. When PG&E decides that it's getting to be one of these high-price days where the system is constrained, they can send price signals or what we call reliability signals. Reliability signals mean the system is getting into a critical stage and the electric system's getting stressed. And actually, you could have rolling blackouts if it gets too out of control. The ISO will actually start rolling, blacking out certain neighborhoods in order to maintain the grid so they don't lose control. So the device here is hooked up to the building controls and will change the temperatures in the building. We might change the light levels. And it's a fully automated system. So the people in the building get to choose how they're going to respond. They change some of the zone temperatures. They change some of the light levels. We have one site where they actually did a bakery, and they bought extra pans. It was Svenhard's in Oakland. They bought extra pans, and they turned off the dishwasher. So we can try it on different devices, and I'm going to give you a bit of an introduction into the devices. This little blue box here is something we used for several years. The first tests we did were back in 2003, and we did Bank of America, UC Santa Barbara, which I'll show you, an Albertsons, which I'll talk about, a GSA building, and Roche Pharmaceuticals. The first year, in 2003, it was only software. We didn't use any hardware. We used a software system called XML, and many of you may know HTML. HTML is like a hypertext language that you see on web pages. XML is called Extensible Markup Language, and it's a machine-to-machine internet signaling platform. And not every building has the ability to host the XML systems. If they didn't have that, we use this little blue box. This little blue box is called a Modbus relay. It has particular protocols, and it only costs about $200. So we deployed these in a number of buildings around the state. We had some we were doing it at Oracle. We had this at Chabot Space Sciences before we used this one. Now, the problem with this box is that you had to poke a hole in the firewall for the internet systems. And it wasn't a good sort of internet-friendly, secure device. This system, however, uses something called encryption and authentication, like your banking system, SSL, so nobody can break into it. So the security that we're using on the internet is very good, and it's a common question that we'll get from people about whether or not the security of the system is a problem or not. Now, it'll only change your set points, so we're not going to turn the building off, but we do care a lot about making sure that the infrastructure that we're building, when the supply and the demand side are communicating, is a secure one. I'm going to tell you a little about this building. This is an office building in Martinez. It's a 130,000 square foot building. And I'm going to walk you through now what the load response looks like in this graph. Now, I know it's a little bit complicated, so let me get you oriented to what you're looking at here. Along the bottom is time. So this is actually June 21st, 2006. I have two axes here. I have the outside temperature of these triangles here. So it got to about 100 degrees. It was pretty hot in Contra Costa. And on this side here, we have whole building power. You can see here, this top line here is how much electricity it would have used. And we have a variety of baseline models that we use to calculate how much it would have used based on a 100-degree day. So we actually do weather regressions to estimate how much power it would use for each 15 minutes based on historical data and weather files. So when the signal came in, the building shed load by resetting the temperature. This particular event was a 6-hour event. So PG&E has what's called critical peak pricing. And from noon to 3 and then from 3 to 6, the price goes up. So the people are actually on a tariff, what's called a dynamic price. And when at noon, the building, they reset the temperature, so they went from 72 to 75. They let the building warm up a bit. And then in the second period, from 75 to 78. And we see a 6-hour shed. We're shedding almost 20% of the load. We're shedding about 100 kilowatts, you can see here. And they did not get complaints. So we're very careful. This is a pretty deep shed. In general, we try to get about 10%. So we've shed electrics. When I say the word shed, we're shedding electric load. This middle bit here is the amount we've shed. You can see the nighttime load. This building gets down to 100 kilowatts. And this is a classic shape for an office building, to have some loads on at night and then to go high up when it's hot outside and down again. There's no peak that happens when the cooling system comes back on again. And this building has participated for many years. We have over 100 buildings in California now use this technology. And we're trying to make it a standard so that all the utilities use a common communication system, and the demand-side buildings are actually listening to these signals and responding when these events occur. And we're actually looking at making this part of the building codes in the future so that the buildings are built this way we don't need boxes. We actually have it in the software. And as part of the Title 24, they would listen to signals and they would automatically reset their temperature. So this is the kind of thing that we do. Now, let me tell you a little about the tariff. In PG&E territory right now, from noon to 3, the price is 3 times the moderate price. And then from 3 to 6 here, it's 5 times the high price. And the way that works is that some of our sites only will do the second 3 hours. They don't have to do the entire 6. And that's what we call price response. And it may be in the future that the prices actually vary each hour and that the buildings are actually responding and changing. And this may come in your home in the future as well. So we'll talk about that at the end of the talk. But that's basically what we're doing, is we're sending signals that change the shape of the electric loads in the buildings themselves. And this shape we see here of it cooling off, the cooling system backs off and comes on again, then backs off again and comes on again, and then no rebound, as I said. This is the library at UC Santa Barbara. I'm going to show you some of the pictures of some of the facilities that we've been working with. We knew Jim Dewey. Prior to this work, I'd been doing a lot of work on information systems that building operators have and what kind of technology they have to understand the energy performance of their buildings. And I'm going to talk a little about the idea of making that energy performance visible, because we know you get a utility bill month to month and you don't really know what your building's doing. And we really want that to change. And that's good for these electric load shedding and for total energy efficiency. This is the Oakland Federal Building, the Ron Dellums building. This is one of them where we actually got a full megawatt of reduction by setting the temperatures up. They had 1,000 zones, different HVAC zones, different ventilation zones. And we actually had to go to the control system, which was the Johnson Controls system, and pre-program the strategy into it so we'd automate the shedding in this building. So this building we got some very good test data out of it back in the early years. And we've been working with several of the General Services Administration government buildings. The government buildings have been excellent partners, helping us understand whether the buildings are ready to receive the signals and whether we can get them to reduce the electric load like we talked about. This is an office building in Sacramento. And I showed you this one because office buildings are one of our hardest targets. The federal building is a government building, but these leased buildings where the tenants actually pay for 72 degrees are very challenging for us because it actually will say in their lease agreement what the services in the building should be. But we've had a few of them, and we're very interested in trying to work with more of the leased offices because they represent a big part. Office buildings are the biggest part of the electric loads in the commercial sector. And the commercial sector in California is similar in size to the residential sector. More than 2/3 of the electricity is in the commercial and residential building sector. Now, this is what an aggregated shed looks like. So this is the aggregated sum of a number of buildings. Each of these colors here is a separate building. This one was quite a large building. This is the Bank of America Concord Data Center. And you can see we stack them up, and we're almost at 12 megawatts here, and we shed about 1 megawatt. So this has the shape similar to what I showed you for that single building a moment ago. And you can see here again, at noon, we reduced the electric load. So the white in here is the reduction. And we can see we reduced the load. We got down to about 10 megawatts. It came up a little bit. We reduced it again. And here we see a little bit of a rebound. But we use the word rebound. When the control systems come on again, they hit a new peak. And certainly when we do that at Target and at IKEA, they still have people there at 6 o'clock, 7 o'clock at night. So they don't turn off until later in the evening. And you can see the shape of the load is much flatter than the other office building I showed you. So we're at 6 megawatts at night, in the nighttime up to 12, and then back down again. So there's only a 50% difference here between the nighttime and the daytime. So depending on what kind of buildings you're looking at and how you aggregate it. But this is what we show to PG&E. So we automate the reduction in the electric loads at these peak times. This is a data center in Concord, the Bank of America one that I mentioned. Now, the data centers are interesting ones because, as many of you know, data centers use a lot of electricity, and they want to be very careful to be sure that they don't interrupt the critical loads. But they actually were working in their office areas at this facility, so we were able to work with them for many years, and they've worked with us for all 5 years. This is a high school. Many of the high schools, kids leave at 3 o'clock, so they do quite well under some of these tariffs. So there's a lot of high schools that have gone on to these programs. IKEA, we've worked with both East Palo Alto, here in Emeryville, and up in West Sacramento. And the West Sacramento one was a very interesting story because at that IKEA, they actually decided that maybe they could do their strategy every day. And people say to us, well, if I do it on a special day, can't I do my strategy every day? And the answer is sometimes you can. And that's why the demand response actually gets people familiar with, is their building even minimized for the outside temperature? So maybe there's more I could do every day. Then it's not shedding load anymore, but it's energy efficiency. So we really get to learn about how can I change my load shape? And if I operate my building different, does it actually save anything? Now, this graph is to show you that California's made a significant investment in the idea that there's going to be a signaling infrastructure. So we're going to be sending signals. And the exciting thing about this is that the supply side, where we supply energy, and the demand side are becoming linked. So while I've been talking mostly about the commercial buildings, which is the area I've done most of my work, we do work in residential and in industrial. Over here in residential, we have something called a programmable communicating thermostat. So the thermostats in the homes will be listening to signals. And those, of course, are the devices that use most of the power on these hot summer days. In the industrial facilities, you can use the same kind of boxes that I have here so that these signals can be centralized to the control system. And we've had a lot of luck using the same kind of technology into larger facilities. And when I use the word we, I'm referring to the work at LBNL has been disseminated through a number of commercial partners around the state, and we work directly with the utilities to try to test these kinds of concepts and deploy them directly with the different utility programs. I'm going to tell you now about Albertsons here in Oakland. This is the store down by the airport. And this store, back in 2003, I mentioned we did 5 sites. And these sites had received what was called enhanced automation money. And really the history of this project was after the electricity crisis, we were asked whether we could get common signals to buildings and whether the buildings, once they received the signals, had strategies that could be somewhat common. And the Albertsons was one of the first sites we worked with because they got access to a $50 million pot of money that the California Energy Commission had allocated to commercial facilities. And what they did was they built this. Now, I know this is a little bit complicated, and I'm going to go through just a few features of it, but what I'm really going to do is tell you the story about the chicken cooker down here. So up here, we have this price server, and we were using the internet, as I've mentioned. So the signals go out over the internet. And for the Albertsons, the polling client, so the people who were working with our software were actually in Florida. And we were at that store one morning in probably June of 2003, and we were on the phone with the folks in Florida, and they were sending the internet signals, and we were looking at what was happening in the building to make sure we had an end-to-end connectivity test. And here you can see the loads. We have the overhead lighting, the freezer anti-sweat heaters, and the freezer case lighting panels. Now, the anti-sweat heaters are, you know, in a grocery store how the refrigerator case doors get foggy sometime. Well, the anti-sweat heaters actually have a heating element in those doors to keep them from sweating. So that's what an anti-sweat heater is. And so an anti-sweat heater is to keep the condensation off of the freezer doors when you open it up and you look for your frozen peas and your ice cream. So for each of the facilities, we drew pictures like this. So we actually drew these graphics of what was talking to what. How was the panels labeled? How was the connectivity working? And how could we test when we were actually fully controlling what we wanted to control? And we were testing the lights, and we were testing the anti-sweat heaters. So the lights were very visible. You can tell California has what's called bi-level switching, and we can turn off 1/3 of the lights, like a patchwork or one of the lamps in the ballast. And so we could turn off some of the lights. And Albertsons used to have this on their grocery bags. We're dimming our lights for you on their grocery bags. Some of the stores kept those lights off all the time, even after the crisis. And then a new manager would come in, they'd turn them on again. So there was some choice in those lights. But what was happening was we were actually walking around, and somebody came up to the manager we were with and said, the chicken cooker's gone off. And the chicken cooker wasn't supposed to go off. And we thought, oh, well, it didn't have anything to do with us. But in fact, it did, because the panels were mislabeled. And this is the electric load shape of a chicken cooker. But it's actually labeled anti-sweat door heaters. So they actually had the circuit labeled wrong, and the control was labeled wrong. So we didn't want to be turning off the chickens, but we were. And so they fixed that. But I literally spent a couple of weeks, because we didn't really know that was a coincidence that the chicken cooker was going off just because we were doing that test. It was really our fault. We were causing it to happen. But this is what chicken cooker load shape looks like. It's off at night. Then they cook the chicken. So each of these squares here is a day. And this is the standby power when they keep the chickens warm. And this is actually cooking the chickens. And I spent a lot of time looking at this to say, what would a chicken cooker load shape actually look like? So all these devices have electric loads. And we're going to, over time, what's going to happen with the internet and more metering systems is we're going to be able to see things like chicken cooker loads. And great for Albertsons for measuring that. They actually measure the lighting, the heating, the ventilation. Walmart does as well. So they sub-meter, that's called sub-metering, and they do it over the internet. So you can actually see what's using power when. And some things you don't want to turn off. And this is an example of that. Now this building is another one I like to talk to, and many of you know, friends of science would know. It's the Chabot Space and Science Center, which is a museum up in the Oakland Hills. And the great thing about this building is you can see it's very massive. See a lot of cement, not many windows. So this has been one of several buildings where we actually studied pre-cooling. So before these events at noon, we actually let the building get a little cooler. And the way comfort works in buildings is the radiant temperature of the surfaces actually influence your comfort. So while the HVAC, the ventilation and air conditioning systems monitor the space temperature, comfort's actually influenced by the temperature of the surfaces as well. So we have been looking at the idea of actually letting the buildings be a little cooler in the morning and a little warmer in the afternoon. And this building has done very well as a pre-cooling demonstration site. In fact, because of where it is in the Oakland Hills, we can actually ventilate it at night with the cool air and use less energy during the entire day as well. So we don't use the chiller in the daytime, but we use the night air, And the pre-cooling strategy to make it more demand responsive is actually the low energy strategy as well. And that's always a good thing. So we don't want to pre-cool and then have cooled the building and then not have the mass used the right way. So that's an important building for us. Now what I just showed you is related to this graph here. And the concept here is that here's where we spend most of our time. People think a lot about energy efficiency, and as many of you know, one of the best ways to handle our problems with CO2 and the energy crisis is to use less energy. So that's daily energy efficiency. We think about the energy use over a day, over a year, and we all think about how much energy we use. But what's happening is for the grid, for the electric grid, we care about when we use energy. We care about the time we use it. We care about what we use in the day versus what we use at night. Because what we use in the day drives that system peak that we've been talking about. We care about the peak. So for large commercial buildings, they actually get special charges for the total they use on any given day over the month, and they get charges for daytime versus nighttime. So we have what are called time of use rates, and those are actually coming for residential folks in California as well. And I'll talk a little about that in a few minutes, but basically people are getting meters where they're going to start charging you a different price for the daytime versus the nighttime, sort of like your cell phone, but when you use energy is going to matter. Over here, day ahead, demand response, day of, real-time demand response, and spinning reserve. So as we go this way, we care about the very moment we're using energy. And the idea of spinning reserve means that on the electric grid, there are power plants sitting in reserve that are ready to be brought on to balance the system out. And that power has a lot of value. So we actually may have buildings that participate in reducing their demand in a very fast time frame, in the seconds to minutes time scale. Whereas if we do it day ahead, I know tomorrow is one of my special days for my orb, and I'm going to get ready for it. But some of the building systems might be able to respond to something in very real time, and the best example is probably what we call a dimming ballast. So lighting systems in commercial buildings are getting to the point where your fluorescent lamps can dim, and that dimming ballast provides daily energy efficiency because it can dim in the perimeter areas, in the areas near the windows when there's enough daylight, and then it can dim even more for these electric shedding for the grid. So what's happening is the control systems and the granularity of the devices, we want the ability for the building systems and to actually be able to respond to these things. Now the other idea here is that when I want my daily energy efficiency to be evaluated, I think about, am I using the right amount given what's happening in the building? Am I overcooling, undercooling? Is it the right amount of lighting? So that's what I mean by service level optimized. And then time of use optimized. Am I doing my laundry at night instead of during the day? Can I do my dishwasher at night instead of during the day? But then service levels temporarily reduced. So we temporarily change our set points. We might change our thermostat, we might change our lights, and we actually give back to the grid in real time. So that's the idea here. And this is research here. We're still, this is not common practice. This is we're trying to get everybody to do, and what we're going to see is more and more people going in this direction to get us even interacting with the grid. Now, when I interact with the grid, I'm going to be better able to do that in the future. And this is a picture of the kinds of components in commercial buildings that we're starting to see deployed in buildings. Here is the domain we're talking about, where we have what's called electric optimization with real-time pricing for multiple buildings. So if I'm Target or Walmart, I want to know what's the price in California and how do I make my portfolio cost minimized. And in fact, Walmart does that in Texas. They use a neural net to predict the next day, and they buy power on the spot market. So they actually shed load when the prices get high, and we're seeing a lot of large companies to do fairly sophisticated things in the electric market. But there's some other things I want you to see here. We have electric chromic glazing and thermal systems with daylighting. So we actually have movable shades. We have heat recovery chillers. light shelves, automated blinds, dimming ballast, which I mentioned, and a variety of things that makes the building more dynamic. The building will be more energy efficient in addition to demand responsive. So it can shed load, but it can be optimized for every day. And then up on the roof, we might have photovoltaics. And the reason that's important is the kinds of things we're talking about in making the building more dynamic is important not only for buying power from the grid, but generating on site. So you might be part of a microgrid where your neighbor has a generator, and you might be buying power from him. So we might have distributed generation, not just buying from PG&E, but actually local supply. So our ability to balance our supply and our demand is going to become more and more important, and technologies like this will help us achieve that aim of optimizing the systems overall. This is my second to last slide. This slide here I'm going to talk about for a minute because this is where it gets really exciting when we look at the emerging technologies in buildings and what we're able to do today and where it might take us in the future. Many of you, especially folks in Berkeley, have heard of the Prius effect. So now that I have feedback on my miles per gallon, I might drive a little differently. And we know that in buildings that might be the case as well. So if people had dashboards and feedback, they actually might be able to understand when they're using energy, how they're using energy, and actually use less energy. And there's a little picture here. This is actually the UC Santa Barbara Physical Science Building, where the electric loads show that the fan was left on all night, and then here we turned it off. So they literally were seeing there were problems with what was on and when things were on. And you can use gauges and dashboards and things like that to help people understand whether or not there might be, whether energy is actually being used in an optimized way. So we might actually have simulation models and things like that, helping us look at the cooling load, how many people are in the building, how many chickens were ordered, and get the right amount of energy. This is my last slide, and I'm going to spend a few minutes talking about this. This is home information and automation. And in California, the electric utilities are putting interval hourly meters on every home, and they're spending a couple $2 billion doing that. Each of the utilities is putting in a slightly different system. San Diego Gas and Electric's putting one in, PG&E, SoCal Edison. And you're going to be able to look at your data over the web. So you're going to be able to look at your load shape, just like I've been showing you some of these load shapes. And eventually you might even be able to look at your dishwasher. So that we care a lot about the protocols for the way the information is exchanged. Just like you're looking at Blu-ray high-definition DVD systems and things like that, there's going to be protocols for whether your washing machine is Zigbee or Z-Wave or 6LoWPAN. So all these new networking systems are emerging now. And California is going to be a place where you start to see devices that can talk to each other to let you know what's on in your house. You can spend $40,000 now for a home automation system, and you can get this kind of information, but it's very expensive. We're trying to move this into common practice, lower the cost, and make it useful to people so that they're actually able to cost minimize their energy systems. Here I actually have an alarm system as well, so that a security system, for example. And a lot of these technologies are coming from other segments of the market, from security, from entertainment, and we care a lot about what's going to happen in California homes. The utilities definitely want you to reduce your space cooling on these hot summer days. And in California, in the Bay Area, that's not a big deal. Most of us don't have air conditioning. But if you go through the tunnel, if you go out to Stockton and Bakersfield and Palm Springs, most people have air conditioners, and that's a big problem. Even pool pumps. We know pool pumps should be done at nighttime. And again, in the Flex Your Power campaign, we all get some messaging, but these kinds of things are coming. It may be even in the future that you have a plug-in hybrid car on your system and you care about when it's charging and when it's not charging. So there's going to be a lot of changes in the homes. It'll come to the newer homes first. It'll come to the bigger homes. It'll come to the inland homes. But here in Berkeley, we do know that people will be interested in getting this technology and helping to use it the best way they can in their homes. So I'm going to stop there, and I think Alan is we're going to take some questions. And I think I'm let you guys ask some questions.
Well, first, let's thank Marianne for her very interesting talk. So we have two options for asking questions. There are a pair of mics right up here at the front of each aisle, and that's one way to do it. And secondly, you can just wave your hand wildly from your seats, and I'll call on you. But I see we have one question here right now, so please go ahead.
This question is kind of not directly about related. I've heard statements that investing in a solar panel in your home is a waste of money or it's literally worthless. What is your opinion?
Well, it's certainly not worthless. A few pieces of advice. They are expensive, which anybody who's looked into the cost of putting photovoltaics on their home would know they're very expensive. First thing to do is to look at how you're using energy. Look at your utility bill, look at your appliances, look at your insulation, and try to think about whether or not you can use less. What happens with solar panels is people size them without doing all the energy efficiency they can do first. So the first thing you want to do is put in as many compact fluorescent lamps and do the very best on energy efficiency, and then it'll make your solar system less expensive. Sure.
Okay. If you turn on and off your appliances, which I do, I actually unplug the TV when I am not at home, or unplug the washing machine. Do you actually ruin the appliance?
That's a really good question, and I don't know the answer.
I actually unplug appliances in my house when I am not there, like the TV, like the washing machines and the dryer. I unplug them from the
wall. I think that's great. So the question was, is it hard on the equipment if you plug it and unplug it a lot? And I think the answer is probably no. It's okay. It's okay to do it. What we want in the future is power strips that make that easy to do. So we do know that the plug loads are creeping up because everybody has their cell phones and their toaster has standby power and everything. These standby, we call them vampires. So that's good that you do that. I can't think of a device where that would be a problem. Certainly, if you have your internet unplugged, you're going to lose connections. But so it's a case-by-case kind of thing.
And the last question.
Sure.
Is there a program wherein there are some sort of a rebate for timing irrigation in farms? You know, you see, when you use a motor to pump out the water, do they have a program?
They actually do. When I showed the homes, the commercial buildings, and the industrial plants and talked about automation, agricultural pumping is a big load in California. So there are time of use rates for agricultural, and there's actually some of these electric load shedding programs for the pumps too. The State Water Project is a huge participant in the electric grid demand response.
Thank you.
Yeah, the compact fluorescence, in follow-up for her question, they aren't really meant to be used in places like back rooms and where you come in, turn them on, 2 minutes later, turn them off. The life is shorter on those. I understand that it is that.
Well, you have to do an awful lot of switching before you're going to hurt that compact fluorescent. So actually, I have some in my closets, and they stay there so long I don't have to change them very often because they're actually not on. So they can probably take a pretty high level of switching. The older ones, that was probably more of a problem, but I do believe frequent switching on compact fluorescents is not a big problem.
You don't make any mention of the lower DC power loads in homes. I mean, every home probably has 10 transformers for cell phone charging and everything. Why is there no seeming effort to have some standardized DC provided every home?
That's a good question. The question was, why don't we have direct current instead of alternating current for these kind of plug-in systems? Because we have a transformer back to DC. And the answer is, it was Tesla versus Edison that had the DC-AC fight. The lab, Lawrence Berkeley National Lab, does have a project right now looking at DC for data centers, because data centers have that same problem that you're converting power and there's significant transformer losses. But you're right, we don't currently have DC distribution, and there are people thinking and looking at it. It would take time to develop that infrastructure.
But it would just mean having every home, and your new homes would have
Right.
a converter on the front end so that they have another plug for all the DC small voltage needs.
Right, it's a good idea, and I've heard the idea, and I don't know the status of what would it cost.
PoE, power over internet,
Right,
power over Ethernet, pardon me, but that doesn't seem to be getting much.
right. It's a good question. Sorry.
Yes, you're working so hard to shed power, and I would think that even though only a third of the power used is residential, solar residential would be helpful in the long term. Why would PG&E decrease the advantage the cost advantage to solar as they have done in January, when I would think that that advantage would also help to bring more people into the solar arena? So why would they do that?
So they decreased, say that again?
Yes, there's an E7, I believe, where the advantage from using peak as opposed to non-peak electricity
Right.
Was given to homeowners with solar power, and that has now been changed and reduced.
Right, and so I think you're talking about designing the electric rates themselves?
Yes.
Yeah, and I'm glad you asked that, because we actually have projects with PG&E and the utilities in California to look at tariff designs and the principles by which we design these tariffs. And it's actually, again, it's a little bit of art and a science and economics. And as I mentioned at one point, the purest pricing would be if the wholesale and the retail prices are coupled. And we might actually start to see that. But the retail prices that you get from PG&E, they go through a variety of design criteria, and they don't, the prices, the tariffs have been changing a lot over time. So like the tariffs are actually flatter than they've been in sometimes. Sometimes the differential between daytime and nighttime has been bigger. So it's actually sort of a research topic in itself that the economists spend a lot of time on, is designing tariffs, because there's winners and losers for these different designs, and there is a policy angle to it. So we are going to continue that debate in California, is actually how to price it, how does that work for solar, how does that work for these dynamic systems.
Why not demand response every day? What are the drawbacks?
Well, we design buildings to typically run at a certain, so the question is, why don't we do the demand response every day? And the answer is because we have levels of comfort and levels of services that we design to, and we don't necessarily have those optimized. So you're right that if you're willing to let your building be at 80 degrees all the time, that's a good thing. And when the call comes to set your temperature up, it's going to be hard for you to do that. So you're right that that's actually a good philosophy, is to be as energy efficient as you can every moment of the day. And can you do even more on these special days? That's the question. Yeah, I don't think I did. Alan reminded me of a story I'd like to tell. Alameda County Water District was one of our best sites that did a very aggressive reductions in their electric use on certain days. And through the electricity crisis in 2006, we had about a dozen sites that were on the automation. None of them turned it off. We had a heat wave, and Alameda County had Hawaiian Shirt Day, and they served iced tea. But they told people, here's what's going on, and we're doing our part. So they didn't actually. We do recommend Hawaiian Shirt Day and iced tea and ice cream.
I don't think this relates directly with your work, but could you speak a little bit about the research that's going on in LBL about in the home sort of sensing research from both a technology perspective, but also just from a psychological perspective?
Yeah.
Are homeowners actually ready to embrace this technology with this kind of mainstream idealism with energy efficiency?
Right. The question was about sensing technology, research, and behavior, as I would say the second part of the question. I'll start with the behavior part. We actually have some projects that look at behavior and belief systems and what do people understand about this and what are they willing to do and how do you message it in a certain way. And actually, the electric utilities have been doing that for quite some time. SoCal Edison has air conditioner cycling programs where they'll turn your air conditioner off, but you get $100 a summer and they'll turn your air conditioner on and off. So, you know, like anything, like people driving Priuses or putting compact fluorescents in your house, there will be parts of the market that are more responsive, and we want to make those parts of the population bigger and bigger. So we do know that this is a paradigm change to be energy aware, and hopefully we're giving people the tools that they'll be able to make good choices. And something I didn't say is a lot of what we do is all about choice. So you get these devices, but then you choose what to do with them. If you want to only do a small amount, that's fine. If you want to do a lot more, hopefully you'll have some financial incentives. On the technology side, we do work with UC Berkeley, with the CITRIS, the Center for Information Technology Research in the Interest of Society. They're doing a lot on sensors and harvesting sensors that don't need batteries. And a lot of work on in the home. Where would you put these sensors? We have this vision of knowing the temperature everywhere, so you can model it and you could predict tomorrow. And so there is a lot going on. Some of it on campus as well. That's a good question also. And again, these tariff designs, they have all kinds of winners and losers. And I don't know about what the utilities are thinking about the plug-in cars. It's obviously very important that you don't set a new peak and things aren't on at the same time, so they would be done at night. I have heard about the idea that you don't want to steal power you don't want people stealing power from you. So there's going to be issues on plugs that are aware of who's plugged into what. So the plugs actually care because that could be quite a load. So there will be technology, I think, emerging when we start plugging cars in. This is something to think about.
Speaking of the Prius, it runs on a three-phase AC motor. Has to charge the battery in DC. What to run a DC motor on?
That's a good question. The question is, why don't they have a DC motor on a Prius? Maybe somebody else could answer that. I don't know. Yeah.
One of the mentions that you made was regarding commercial buildings using a third of the power. And that's kind of a set which is managed by a few people. And apart from the lease constraints, what do you see barriers to adoption and what's being done for that?
For commercial buildings?
Yeah.
Well, you know, commercial buildings, the more precise technical term is non-residential. So anything that's like a campus or a hotel or a government office or a school. So it's a big class of buildings. And what you do in those different sectors depends a lot on how sophisticated the energy managers are. And the utilities have energy efficiency programs targeted at the different market segments. So, for example, we haven't done this in hospitals at all yet. Because now some people do try, but we've been very cautious. We study the strategies. One thing I didn't mention was Target, where we actually measured the volatile organic compounds and the aldehydes if we change the ventilation, because there's a lot of pollutants that come in from furniture, like an IKEA, and computers and tires. So you're actually not ventilating for carbon dioxide like in an office, but you're ventilating for health. And I'm glad you mentioned that, because we do when we do the building science side of what does it mean to deviate from the set points, we care a lot about the occupants. And people can actually do better with temperature changes than ventilation, where they might have asthma or other health effects.
I'll give a comment and a question. The comment is, I'm actually an energy consultant by profession, and in work I've done for the City of LA, the lab has published papers on that trade-off that several people have asked about between rate design and photovoltaics. And you guys have done great work.
Right.
People have been very impressed by looked at specific rate structures for DWP and how that affected solar.
Uh-huh.
My question, which is totally different, is about your talk. Do you have any sense in the aggregate of the sort of savings over time that you can see? I'm involved in a case now with San Diego Gas and Electric, where they're talking about over the next decade saving 4% off the peak they would otherwise have from price responsive demand response and 1% more from dispatchable demand response.
Right.
Do those numbers seem reasonable, small, big?
No, those are right. Actually, again, I'm glad you asked the question because I didn't mention it. But his question was, what's the magnitude of the savings potential for demand response or electric load shedding? And in fact, the Public Utilities Commission has a 5% price response goal. So if we use 50 gigawatts, then we want about 5% of that, which would be 2.5 gigawatts. So we do have price response goals in the state, and we believe they're very achievable. One of the ways they're going to become common practice is when these electric tariffs change. So the utilities are moving towards a time where everybody's prices change through the day, and for commercial buildings, this concept of critical peak pricing is about 10 days a year, these prices go up. And we might see that in homes as well, that 10 days a year, the price is higher than other days. So it's a combination of pricing and technology and behavior and awareness, and we think it's achievable.
What are the environmental
Yeah. Yeah. I'm glad you asked that question also because it's a very non-trivial. The question was, what's the environmental consequences of this kind of technology? Well, first of all, everything we did was shedding load. I didn't talk about shifting, although the pre-cooling is shifting. If we shift from daytime to nighttime, the environmental consequences depend on the generation of daytime versus nighttime. So in some parts of the country, whether coal is in the base load or the peak load will influence the environmental. If you shift to nighttime, either the nighttime is cleaner or dirtier. In California, it's typically fairly clean because a lot of the renewables will be on at night and such. So in California, shifting to nighttime load is typically a good thing, and we could be reducing CO2 overall. So shifting and shedding. Shifting is moving it to the nighttime using the same amount. Shedding is taking a notch out of the load shape, and it's always good. So it's always good. It's environmentally positive in California.
Maybe following on that, I'm not sure. I was struck by your comment when you talked about this last slide about the investment of, I think, $1 to $2 billion on the part of the utility companies in getting automated systems for the capacity for automation in the homes. And you mentioned that each of the utility companies was doing their own.
Yes.
And I wonder, are these interoperable systems?
Right.
What does it suggest for
Right.
being able to manage loads across the state or across the country?
Right.
Should we be worried, or what's behind that?
Right. Well, that's actually, so the question is, are the systems interoperable among the utilities, and what are the consequences for consumers? And that's actually something that we look at, because the Public Utilities Commission evaluates the utility filings, and there is Southern California Edison and San Diego Gas and Electric are supporting a Zigbee-based networking system, and PG&E hasn't decided. I would like to make a clarification. The utilities are currently installing electric meters. It's called the advanced meter infrastructure. So they're putting the hourly meters on every home. The home automation is a little bit of a separate system, and whether or not the meter talks to the systems inside the house or not is in debate, whether there's a gateway type device. But it is a problem that it's like anything between Microsoft and Apple, that we have these interoperable systems, and we try to do our best to understand the technical benefits of the different approaches, but the market may not always choose the lowest cost technology. We'd like to understand what it is, but it's hard to predict the market for some of these devices.
As a residential user, when will I know my real-time use? You say, will that be available, PG type 2? What about nighttime
Yeah. Well, the utilities will be rolling out the hourly meters over the next 5 years. So they're first doing it, PG&E's first doing it in Fresno and Bakersfield, where it's really hot. Then they're trying out what's working, and so it'll be within the next 5 years you'll probably get it. I liked your question about lights in commercial buildings, because buildings, it's a kind of a joke. They actually used to keep the building warm by keeping all the lights on. So it was in the 70s where, the 60s and 70s where, you know, electricity was too cheap to meter, and we did use lights. People used computers as heaters, you know, near their feet, and all sorts of wrong uses of energy. But so it is something that's very common. Lights get left on, and that's, again, about controls. You certainly need security lighting, and people are cleaning, but lights do get left on a lot. You know, Alan, I realize there's one more slide. I didn't go to the very last one. Go ahead. And actually, I'll do it. I'll do it.
Sponsors, thank you.
Yeah, but we can take more questions if you want.
Okay. Over there, sir?
Yes, where can you get access to PG&E's average emission factor by time of day?
You know, the question is the emission factors by time of day by PG&E. I know that there's a company called E3 in San Francisco, Environmental Energy Economics, and they have something called the standard practice methodology that has these adders for every hour of the year for PG&E. So there are, I think I would look at E3 and the standard practice methodology.
Over here?
I knew somebody that was helping to design the new campus in Merced, wherever it is.
Yeah.
And I'm asking him about using these efficient lights, and he hadn't even thought of the idea. Do you know whether or not the new campus is going to have good lights or not?
Oh, I'm sure it does. The UC Merced, we've been tracking that a little bit, and I'm sure, you know, good lights is there's all kinds of good lights. So I'm not exactly sure when you ask about if Merced's using good light.
About the dorms, you know, whether or not they have these kind of lights in them. He said no. So
I see, yeah.
5 years ago.
Yeah, I don't know.
They do have awnings and also a lot of those devices that you showed in your drawing.
Yeah.
There are a lot of those.
Over there?
A lot of the difficulty is due to power transmission rather than power generation. Am I correct?
That's true. The question was, is that your question?
No. If that's the case, are we looking into power storage devices?
That's a good question also. So the question is about, is the problem transmission, and if so, are we looking at storage? Storage there is research in storage, electric battery storage, flywheel technology, and actually using the buildings as storage. So some buildings use ice and chilled water at nighttime, so they do their cooling, they build some storage and then use it in the daytime. So the tariffs influence the cost effectiveness of that. And storage is an active research part. I'm funded by the Public Interest Energy Research Program at the California Energy Commission, and they have storage research as well.
When Albertsons and Walmart and all of them build new buildings, it's in their interest to put in all of these saving things.
Right.
But especially in residential and small manufacturing plants, I think of manufacturing, just any small business. What's the trade-off of the amount of energy used between old stuff and new?
Yeah, that's a good question. The question is, how do old buildings and new buildings compare? Actually, a lot of new buildings use more energy because they have more services. So their ventilation levels may be higher, even though the energy per square foot for an end use might be less. So it's not a trivial comparison. Some of our old schools, built in the 50s, are great passive, good mask, good clerestory windows. So some of the concepts in the 70s are like the worst buildings. So we actually know a little about the vintages of when the heating, ventilation, and air conditioning controls were the worst. And we're getting back again. You can build buildings today that use half as much as a typical new building. So there are definitely buildings where people have gone the extra mile. In San Francisco, the new federal building is passively ventilated and passively cooled. And San Francisco is a good place to do that, but it actually has airflow windows, controlled windows, and a hollow plan building where a lot of people are near windows, a lot of good daylight. So there's some principles of good design that many architects and engineers are embracing in their design.
I was struck by your comment that you're limited in what you can do in public building or in privately owned buildings because there are these clauses in the leases. Is anybody lobbying the legislature to make that practice illegal?
So the question was, are we making it illegal to have these lease structures that maintain a certain comfort level? And no, what we are doing, the Building Owners and Managers Association asked us if we made it an emergency, they could say the lease is no longer valid during an emergency. So they wanted some sort of a legal way to say, oh, we're not bound to our lease requirements at this special day. It's an area we've thought about. I don't think there's much being done. There is more tenant sub-metering happening, so there's certain things happening, but it's still an issue.
Yeah, would solar generation be efficient managing the peak problem compared to other things?
Right. Well, you know, solar certainly peaks on peak. And that's a good question, but a good thing. But it is expensive. So when we look at supply side and demand side alternatives, often what we're doing here, you know, while solar has good economics in the peak hours, doing this is actually even better because sometimes it spills over to everyday use and it'll lower the whole curve. Again, those peak hours are so important. Those are really cooling hours. And so you could have some solar in those hours, but those peak cooling hours are still a problem. And while the solar is going to help, we see this load growth continuing for many years out.
Last year or so, we learned about the energy efficiency project to have, when you walk into a room, the light automatically goes on. You never turn on or off the switch.
Mm-hmm.
Now, is that kind of thing making progress? Will we expect to see it? And can homes be retrofitted to do that?
Mm-hmm. So the question was, are we going to see occupancy sensors in homes? And I do think you can probably get them now, but again, they're expensive. In commercial buildings, they're very common, of course, in bathrooms, in conference rooms. In my office has one. So they're becoming more common, and I think the price will come down. So a lot of these wireless sensors, you need that sensor has to be installed. It has to be hooked up to something. It has to be calibrated. It has to be pointing in the right direction. So all these kind of intelligences, I do think that you're going to see more and more of it.
Where can I get the glowing orb?
You know, I think they're about. You have to sign up for a demand response program, so the commercial buildings can get them. So he wanted to know where he can get one of these, and I think they're about $1,000. So PG&E doesn't give them out. So I'm very careful with my orb that it doesn't break. I know somebody's broken their orb before. But Brookstone, they were from Brookstone. They're, again, these stock trading, and you can actually. PG&E has about 6 different demand response programs. And there's different orbs for different programs. The signals are a little different. So I think if you put ambient, what is it? There's a website here, www.ambientdevices.com. So.
Well, let's thank Marianne one more time.